Hey everyone, welcome back to the channel. Today we're doing a deep dive into the ultimate machine learning algorithm selection guide. I'm going to walk you through every single decision point with real-world examples so clear that even if you're just starting your ML journey, you'll know exactly which algorithm to pick for any problem. So grab a coffee and let's get started. First, let's understand the main framework. Every machine learning problem starts with one fundamental question. What type of task do I need to perform? There are four main categories, and I'll show you exactly how to identify which one you're dealing with. Part 1. Regression. Predicting continuous values. What is regression? Regression is when you're trying to predict a number, a continuous value. Think of it like this. Predicting house prices, $250,000. $340,000, $180,000. Forecasting tomorrow's temperature, 72 degrees Fahrenheit, 85 degrees Fahrenheit, 43 degrees Fahrenheit. Estimating a person's salary, $45,000, $78,000, $120,000. The key question is linear or nonlinear relationship. Linear relationship example. Imagine you're predicting house prices based on square footage. If houses consistently cost $100 per square foot, then 1,000 square feet equals $100,000. 2,000 square feet equals $200,000. 3,000 square feet equals $300,000. This is a straight line relationship. That's linear. Nonlinear relationship example. But what if house prices don't follow a straight line? Maybe location matters, beachfront versus inland. Age affects price differently for antique versus modern homes. Square footage has diminishing returns. Going from 1,000 to 2,000 square feet adds more value than going from 4,000 to 5,000 square feet. Decision path for linear relationships. If linear plus few features, no multicollinearity issues, equals linear regression. Example, predicting car fuel efficiency based on engine size. Simple, direct relationship. If linear, but many features or multicollinearity issues. Ridge regression. Use when all your features matter somewhat. Example, predicting house prices with 20+ features, size, bedrooms, bathrooms, age, etc., where some features are related to each other. Lasso regression. Use when you want automatic feature selection. Example, predicting student test scores with 50+ possible factors, but you suspect only 10 to 15 actually matter. Decision path for nonlinear relationships. Polynomial regression. When you suspect the relationship follows a curve. Example, predicting crop yield versus fertilizer amount. Too little gives poor yield. Optimal amount gives great yield. Too much actually hurts yield. Curved relationship. Decision trees, random forest. When you have complex rules. Example, predicting house prices where the logic is, if neighborhood is downtown and bedrooms are greater than 2, then price is high. But if neighborhood is suburban and bedrooms are greater than 4, then price is even higher. Part 2. Classification. Categorizing data. What is classification? Classification is putting things into categories or classes. Email, spam or not spam. Image, dog, cat, or bird. Medical, disease or healthy. Customer, will buy or won't buy. Binary versus multi-class classification. Binary, 2 categories. Spam/not spam. Pass or fail, buy, don't buy, fraud, legitimate. Multi-class, multiple categories, dog, cat, bird, fish, beginner, intermediate, advanced, red, blue, green, yellow. Binary classification decision path. Question, are the features linearly separable? Example of linear separation. Imagine classifying emails as spam/not spam based on two features: number of exclamation marks and number of all caps words. If you can draw a straight line that separates spam/non-spam, use logistic regression. Example of nonlinear separation: classifying images of dogs versus cats. The relationship between pixel values and the answer is incredibly complex. No straight line can separate them. Use SVM with RBF kernel or random forest. Question: do you need probabilistic outputs? Yes, logistic regression or naive Bayes. Example, medical diagnosis, where you need to say 70% chance of disease, not just disease or no disease. No, SVM. Example, simple spam filter, where you just need spam or not spam. Question, is simplicity or efficiency important? Yes, naive Bayes. Example, real-time spam filtering on mobile devices. You need fast, simple algorithms. No, more complex methods like random forest or neural networks. Multi-class classification. Are the classes mutually exclusive? Yes. Regular multi-class. Example, classifying animals. An image can't be both a dog and a cat. Use random forest, multi-class SVM, or neural networks. No. Multi-label. Example, tagging photos. One image might be tagged as sunset, beach, and vacation. Use multi-label classification techniques.
Part 3. Time series forecasting. What is time series forecasting? Predicting future values based on historical data over time. Stock prices tomorrow based on past prices. Sales next month based on historical sales. Website traffic next week based on past traffic. Short-term versus long-term forecasting. Short-term, hours to days. Question: are there enough data points for learning? Yes, ARIMA. Example: predicting hourly electricity demand with 2+ years of hourly data, 1,752+ data points. No, exponential smoothing. Example: predicting daily sales for a new product with only 3 months of data. Long-term, weeks to years. Question: do you have complex patterns and lots of data? Yes, LSTM or neural networks. Example: predicting monthly sales with seasonal patterns, trends, and external factors like holidays, weather, economic conditions. No, simpler methods like ARIMA or exponential smoothing. Part 4. Clustering, grouping unlabeled data. What is clustering? Finding hidden groups in your data when you don't know the categories beforehand, like customer segmentation for marketing, grouping similar news articles, or finding patterns in gene expression data. Key questions for clustering. Do you expect spherical clusters of similar size? Yes, K-means. Example: grouping customers by income and age. You might expect roughly circular groups of similar sizes, like young and low income, young and high income, old and low income, or old and high income. No, DBSCN or hierarchical clustering. Example: grouping GPS coordinates of crime incidents. Crimes might cluster around specific streets or areas with irregular shapes. Do clusters have complex forms or distinct density? Complex forms, DBSCN. Example: grouping astronomical objects where star formations might have irregular, elongated shapes. Distinct density, hierarchical clustering. Example: organizing products in an e-commerce site where some categories have many subcategories, like electronics, phones, smartphones, Android phones, while others are simple. Part 5. Dimensionality Reduction and Visualization. What is dimensionality reduction? Taking data with many features and reducing it to fewer features while keeping the important information. Reducing 1,000 pixel values in an image to 10 key features. reducing 50 customer survey questions to 5 key personality traits. For visualization, is variance preservation important? Yes. PCA, Principal Component Analysis. Example, analyzing customer survey data where you want to see which questions explain the most variation in responses. No. T-SNE or UMAP. Example, visualizing how similar different music genres are. You care more about seeing clusters than preserving exact mathematical relationships. Part 6. Generating synthetic data. What is synthetic data generation? Creating new, artificial data that looks like your real data. Generating fake customer profiles for testing. Creating synthetic medical images for training. Producing realistic text for language models. Type of data to synthesize. Images, GANs, or diffusion models. Example, creating realistic photos of people who don't exist for privacy-safe testing. Text, transformers, like GPT models. Example, generating product descriptions, customer reviews, or chat conversations. Tabular data, tabular GANs, or Bayesian networks. Example, creating synthetic customer data with realistic relationships between age, income, spending habits, etc. Part 7. Special scenarios. There were several special cases that are crucial to understand. Small data sets, few features, low sample count. Example, you have data on 50 customers with 5 features each. Use naive Bayes or logistic regression. Avoid complex models like neural networks. They'll overfit. Missing values in your data. Example, customer data set where some people didn't provide their age or income. Some algorithms handle missing values naturally. Random forest can work with missing data. XGBoost has built-in missing value handling. Others require pre-processing. Linear regression, you must fill in missing values first. SVM needs complete data. Interpretability requirements. Example, medical diagnosis system where doctors need to understand why the model made a decision. High interpretability, decision trees. If age greater than 65 and blood pressure greater than 140, then high risk. Low interpretability, but high accuracy. Neural networks, very accurate, but can't explain the reasoning. Random forest, good accuracy, but moderate interpretability.
Part 8. Real-world decision examples. Let me walk you through some complete examples. Example 1. E-commerce recommendation system. Task, predict if a customer will buy a product. Binary classification. Data, customer age, browsing history, past purchases, mixed linear, nonlinear patterns. Requirements, need probability scores for ranking. Choice, logistic regression for interpretability or random forest for better accuracy. Example 2, house price prediction. Task, predict house price. Regression. Data, size, bedrooms, location, age. Nonlinear relationships, location has complex effects. Requirements, good accuracy, some interpretability. Choice, random forest or XGBoost. Example 3, customer segmentation. Task, group customers for marketing. Clustering. Data, purchase history, demographics. Expectation, customers might form natural groups, but not necessarily circular. Choice, try k-means first, then hierarchical clustering if shapes are complex. Example 4, fraud detection. Task, identify fraudulent transactions. Binary classification. Data, transaction amount, time, location, merchant type. Requirements, high accuracy, handle imbalanced data, few frauds versus many normal transactions. Special consideration,
Fraudulent patterns are often nonlinear and complex. Choice, random forest, or XGBoost with special handling for class imbalance. ASHAKE 9. Practical implementation tips. Start simple, then iterate. 1. Begin with the simplest algorithm suggested by the flowchart. 2. Establish a baseline performance. 3. Try more complex algorithms if needed. Always validate with proper train-test splits. Consider your constraints. Computational resources. Neural networks need more power than linear regression. Training time. Some algorithms train in seconds, others take hours. Prediction speed. Real-time applications need fast prediction algorithms. Memory usage. Mobile apps need lightweight models. Data preprocessing matters. Scaling. Many algorithms need features on similar scales. Encoding. Convert categorical data like red, blue, green to members. Feature engineering. Sometimes creating new features is more important than choosing the right algorithm. Conclusion. This flowchart is your roadmap, but remember, 1. Every problem is unique, so use this as a starting point, not a rigid rule. 2. Experiment with multiple approaches. The best algorithm might surprise you. 3. Domain knowledge beats algorithmic complexity. Understanding your data is more important than using the fanciest algorithm. 4. Simple often wins. A well-tuned simple model often beats a poorly tuned complex one. The key is understanding what each algorithm assumes about your data, then matching those assumptions to your specific problem. With practice, this decision-making process becomes intuitive. That's the complete breakdown of choosing machine learning algorithms. This flowchart covers probably 95% of the decisions you'll face in real-world ML projects. If this helped you, smash that like button and subscribe for more detailed ML content. Drop a comment with a specific problem you're working on. I'd love to walk through the decision process with you. Next week, we're diving into hyperparameter tuning strategies for each of these algorithm families. Until then, happy modeling.